Hey guys, welcome back to another round of chemistry notes. In this video, we are going to talk about ionic nomenclature, or put another way, how to name things that are made of ions. So before we can name things that are made of ions, we first have to remember what ions are. So remember that ions are atoms, or groups of atoms, with positive or negative charge. And again, that charge comes from either gaining or losing electrons. So there are two types of ions. There are cations, and you may recall from Unit 4 that cations are positive. The way to become positive is to get rid of negative electrons. So your positive ions are positive because they have lost electrons. Negatives go away and you are left with a positive charge. Your other type of ion is the anion. These have negative charge. And again, you can think of the N in anion as being N for negative, or you can think about the crossbar in the A as being a negative sign. In any case, you need to know that anions are negative and cations are positive. And your anions are negative because they have gained negative electrons. If you pick up more negative things, you will have a more negative charge. You also need to remember that nearly all of your representative elements consistently form the same charge. Remember that for your alkali metals, everything in this first column forms a +1 charge. And your alkaline earth metals, everything in group 2, that's going to form a +2 charge. In all of Unit 4, we skipped all of your transition metals. We're going to skip them again now because they are not representative elements. Everything in group 3 forms a +3 charge. Then we kind of skip the column that starts with carbon because it does weird things. And then the column that starts with nitrogen, those are -3. The column that starts with oxygen is -2. Your halogens, which start with fluorine, are -1. And then your noble gases don't form a charge because they are happy with their number of electrons. So this is a pattern you are going to need for the rest of this unit and really for the rest of the year. You need to know this +1, +2, +3, skip, -3, -2, -1, skip. And it'll be easier to remember, maybe, if you remember this is happening because all of your elements want to be like a noble gas. So if fluorine gains 1 electron, it'll be like neon. If oxygen gains 2 electrons, it will be like neon. So the charges are the result of gaining or losing electrons to be like a noble gas. There are 3 major types of ionic compounds we are going to learn to name. They really all follow pretty much the same rules, but you should kind of know the differences. A binary ionic compound, this prefix bi, like a bicycle, means 2. A bicycle has 2 wheels, so a binary ionic compound is made of 2 elements. If you have an ionic compound that is made of 2 elements, one of them will always be a metal, and that metal will always form the cation. It will always be positive, and one of them will be a nonmetal. And the nonmetal will form the anion. The nonmetal will be negative. So those are your binary ionic compounds. They're made of exactly 2 elements. A polyatomic ionic compound is made of at least 1 polyatomic ion. So these are the things we've been memorizing since day 1. Your Nick the Camel stuff, it's finally going to come into play. Your polyatomic ions are things like nitrate and phosphate and chlorite and hydrogen carbonate, which is new this 6 weeks. The polyatomic ion in your ionic compound could be the cation, could be the positive thing. That's pretty rare, but it is possible. It could be the anion. That's more common. Or it could be both. You can have two polyatomic ions together making an ionic compound, but anything that is made of ions is ionic. And your third type of ionic compound is hydrates, are hydrates. These are ionic compounds that contain water within their formula. This is not something dissolved in water. This is like a crystal structure of an ionic compound that has some water trapped inside of it. The water is inside the ions, not the ions being inside of the water. We'll talk more about this a little bit later on, but just for now, remember that hydrates are a thing, and we will come back to them. As far as naming standard ionic compounds, pretty straightforward, normal things. The rules are simple. To name a standard ionic compound, name the cation. The cation will always come first, right? The cation is positive, and you should always put your positive foot forward. So the cation will come first. If it is monatomic, monatomic meaning made of one element, one atom. If it is monatomic, if it's just a metal, sodium, copper, potassium, rubidium, if it's just one thing, just one metal, state the name of the metal. Just say, hey, this is zinc. So then you say zinc. That's if it's monatomic, one element. If it is polyatomic, if it's one of your polyatomic ions, then you will just state the name of the ion. So once you've decided it's an ionic compound, the first thing is really easy to name. You just say its name. Name the first thing. Once you have named the first thing, you will name the second thing. The second thing will always be the anion. The negative thing will always go in the back. If the anion is monatomic, made of one single atom, one single element, I should say. If it's something like sulfur or nitrogen or oxygen, you will keep the root of the element just like you did for covalent naming, but then change the ending to "ide." Again, just like we did for covalent. So instead of oxygen, you would say oxide, and instead of sulfur, you would say sulfide. That's if it's monatomic, one single thing from your table. If it is polyatomic, something like phosphate or nitrate or bromite or perchlorate, if it is a polyatomic ion, just identify the ion and state its name. Just name the ion. And one last very important thing about this before we see some examples. In ionic compounds, there are no prefixes. This is like the number one mistake that people try to make. They will try to keep using their prefixes once we have moved from covalent to ionic. Prefixes are for covalent compounds. There are no prefixes in ionic, so please don't try to use them. All right, let's go ahead and look at some examples of this. All right, our first example is NaCl. We can tell this is ionic because sodium is a metal and chlorine is a nonmetal. So to name this, we will name the first thing. This is monatomic. It's sodium. You can look on your table. Na is sodium. So to name this, we will just name the first thing, sodium. And then we will name the second thing. Our anion is monatomic. It's just one element from the table. So we will keep the root, chlor. Then we will change the ending to IDE. So NaCl is sodium chloride. That's just table salt. All right, looking at our next one, we have AlPO4. Again, Al is a metal And PO4 is one of your polyatomic ions. So that is a pretty good sign that this is an ionic compound. So we will name the cation first. The cation is just a metal, it's just aluminum, so we will say aluminum. And then we will name the anion. The anion this time is one of our polyatomics. It is phosphate. And you might be thinking, but Miss Childs, phosphate is PO4 3-. And you would be right, but if you look at all of these compounds, actually none of them have their charges present. So we're going to figure out what is happening to this here in just a second. But for right now, you should know that if it is PO4, it has to be phosphate. This 4 is what identifies phosphate. If it were PO3, we would know that it's phosphite. So if you see the base of any of your polyatomics, that is the polyatomic ion. PO4 means phosphate. So Al, PO4 means aluminum phosphate. Moving right along to our next example, we have NaBrO. So once again, we'll identify the first thing. This is a metal. It is sodium. So we will write sodium. And then everything we are left with, this BrO, has to be our anion. So BrO is going to be one of our polyatomic ions. Maybe you would recognize it better with a 1- charge. This is hypobromite. So Na is sodium, BrO is hypobromite. So NaBrO is sodium hypobromite. Moving on to our next one. If you think you got it, pause the video, try it, and then unpause the video. Our first element here is calcium. That's a metal, so we can just say calcium. And then everything after calcium has to be our anion. So we have a P here. There is a 2 attached to it, but since it's just the P, that means that it's coming from our periodic table. It's just a phosphorus that has a charge to it. So we will write the root of phosphorus, which is phosp, and then tag on that IDE ending. So we have calcium phosphide. On to our next one, number 5. Out front we have Mg. That is a metal, so we can just write magnesium. And then everything that's left is ClO4, and that's all in parentheses with a 2 on the outside. So for right now, we're going to ignore that 2 because it just means we have 2 of this thing. And this thing, ClO4, hopefully you recognize, is perchlorate. So MgClO4 2 is magnesium perchlorate. All right, last example here. We have LiS. So we'll name our first thing. It is a metal. It is lithium. So we can just write lithium. Our second thing is just one element. It's from our periodic table. It's based on the element sulfur, but it's an anion. So we will change the ending to IDE. So LiS is lithium sulfide. All right, awesome. Let's move on and talk about going the other way. Talk about taking the name and writing the formula. All right, so before we practice writing the formulas, we're going to throw back to the very beginning of the school year for just a second, because before you can write the formulas, you need to remember that the subscripts in a chemical formula show the number of atoms or ions that are present in that compound, right? It's like a recipe. So keeping this in mind, let's look at our steps for writing our formulas. Step number 1, to writing the formulas for ionic compounds is to first write the formulas for the cation and the anion separately. And this will keep you from making any silly mistakes. Remember to include your charges. The charges are the driving force behind this whole thing. So if you forget about your charges, you're done. So that's step one. Figure out what your cation is, figure out what your anion is, and then write them down. Once you've done that, decide how many of each you're going to need to make their charges add to 0. Your cations and your anions will combine in really specific numbers so that all the positives from your cations and all the negatives from your anions get together and cancel out. Step number 3 is to write the cation first. Remember, the positive always goes first, so the metal will go first, and then follow it with a subscript to show how many are present of your cation. So if you need 4 lithiums, you'll write Li and then a 4. If you need 37 potassiums, which you won't, but if you did, you would write K and then 37. So you'll write your cation and then you will write your anion second. That'll be your nonmetal or maybe a polyatomic ion, and then you will follow that with a subscript to show how many of your anions are present. And one more note, please remember that if you need more than one of a polyatomic ion, you'll need to put that formula in parentheses. So earlier we had an example with perchlorate, but it was written as ClO4 in parentheses and then a 2 on the outside. What that meant is that we needed 2 of our perchlorates in that formula. So if you need more than one of a polyatomic ion, you'll put it in parentheses and then show how many you need, because otherwise you end up with ClO42, and it looks like you have 1 chlorine and 42 oxygens, which is, again, not a thing. All right, so let's see some examples of this. Our first example is calcium oxide. So we will start. Step 1 is to write the formulas for the cation and the anion separately. So calcium is Ca. Hopefully you recall that calcium is an alkaline earth metal. Just like we said earlier in the PowerPoint, all of your alkaline earth metals form a 2+ charge. And oxygen, or oxide, comes from oxygen, but it is specifically an oxygen ion. And if you look on your periodic table or flip back in your notes, you will see that oxygen always forms a 2- charge. So we have 1, 2 positives from our calcium and 1, 2 negatives from our oxygen. And these will get together, they will cancel out to 0. And we only needed 1 calcium and 1 oxide to make that happen. So to write our formula, we will write Ca and then O. So this is how you write the formula for calcium oxide. You could, if you were so inclined, put a 1 here and a 1 here. That's not wrong, it's just already implied. If you do not see a number following an element, the implication is that there is one of that element. So Ca1O1 is fine, but CaO is a little faster to write and a little more succinct. All right, that's our first one down. Let's take a look at our next one. We have magnesium fluoride. So magnesium is Mg. Again, looking at your table, it's another alkaline earth metal, which means it has a 2+ charge. Fluoride is F, but the ide tells us it's an ion, So it's going to have that 1 minus charge that all halogens have. So we have magnesium with 2 positives, and we have fluoride with 1 negative. Well, that's not going to cancel out. We have too many positives. So what we can do is add a second fluoride. That'll give us a second negative, and then these charges will cancel. So that means that we need 1 magnesium. We'll write Mg1. And we can have, or we're going to have 2 fluorides. So F2. Again, you can write this one or not write this one, whatever your heart desires. Just please make sure you understand that you generally won't see the 1. When you're given a formula, it will look like this, not like that. All right, next example is aluminum sulfide. So aluminum is Al, and it forms the 3+ charge. Sulfide is S with a 2- charge. You are welcome to keep showing your pluses and minuses if you want to. I'm going to start showing this in a little bit of a different way. I can tell by looking at this that aluminum we are going to need 2 of, and sulfide we are going to need 3 of. And I can prove this by saying that I have 2 of my aluminums, and those each have a positive 3 charge. I can add that to my 3 sulfides, which each have a negative 2 charge. So if I do this math, 2 times positive 3, that's 6, plus 3 times negative 2, that's negative 6, and those will add up to 0. So that's how I know I've done this correctly. And I can say that I need aluminum, I'll need 2 of those, and sulfide, I will need 3 of them. You may at this point have picked up on a trend. If you see it, you are welcome to use it, but I'm not going to teach it to you because I tend to notice that when you explain the trend to someone who doesn't understand it already, it kind of confuses them more than it helps. So if you see the trend, awesome, use it. If you do not see it, that's fine. You can always solve this out like this. So we'll take a look at our next one here. We have magnesium, which is Mg2+, and phosphate, which is PO4 3-. We are going to need 3 magnesiums and 2 phosphates. Important point, phosphate is PO4, and then this whole thing, this group of atoms has a 3 negative charge. Not each oxygen, but the charge of this whole thing is a 3-, a 3 negative. So if we have 3 of our magnesiums, and they each have a positive 2 charge, and if we have 2 of our phosphates, and they each have a negative 3 charge, that will work out to 0. And it means that we need 3 magnesiums, so Mg3, and we need 2 phosphates. So this 4 is attached to this oxygen, phosphate is PO4, and we need 2. So we'll put it in parentheses and say we need 2 of them. Our next one, sodium phosphite. Sodium is Na+, phosphite is PO3, 3-. So we are going to need 3 sodiums, each with their positive 1 charge, and we are going to need 1 phosphite with its negative 3 charge to make everything cancel out to 0. So to write this, we will write Na3 to show that we need 3 sodiums, and then PO3 to show we just need the 1 phosphite. Since it's just the 1, we don't need to put it in parentheses. Number 6, ammonium nitrate. Ammonium is a polyatomic ion. You have not learned it yet. The reason I want to show you this problem is because ammonium is NH4+. It is the only polyatomic cation that you are going to learn all year. so I want you to see it now. Ammonium is NH4 plus, nitrate is NO3, 1 minus. And again, that means that we have a nitrogen attached to 3 oxygens, and then this whole collection of atoms has a single 1 minus charge. A lot of people try to say that nitrate is a nitrogen and an oxygen with a 3 minus charge. No, the 3 describes the number of oxygens, not the charge. So then we have 1 positive from ammonium, and we have 1 negative from nitrate, and that's all we need to come up with. So to write this formula, we will write our single ammonium, NH4, and then we will write our single nitrate, NO3. And the reason I want you to see this is because there are no metals in this compound, but it is still ionic. So if you start a compound with NH4, there's a really good chance that compound is going to be ionic, even if you don't see any metals in it. All right, so keeping this in mind, do those 8 practice problems at the bottom of the page. Pause the video, work the problems. When you're ready to check your answers, go ahead and unpause. All right, hopefully this is what you got. If it isn't, go back and see if you can figure out where you went wrong. If it is, go ahead and move forward. We're going to talk about transition metals and what to do with those, because their rules are just a little bit different. All right, when you are talking about ionic compounds that contain transition metals, before we can do that, we have to remember what transition metals are. Remember that your transition metals are the metals found in the F and D blocks of your periodic table. So that middle section that we ignored earlier, and those 2 rows down at the bottom of the table. Your transition metals are a little different from your representative elements because they can form more than 1 charge. They have what is called variable charge. Instead of always and forever being a +1 or a +2, sometimes it's +1, maybe it's +2, maybe it's +4, it just changes. So you are going to have to say what the exact charge is of that metal at any given time. At this moment, we are talking about copper with a 2+ charge, or we are talking about lead with a 4+ charge. And to show that you're doing that, to show the charge, you are going to use Roman numerals. So a little review on Roman numerals. 1 is I. 2 is I. 3 is I. 4 is IV. 5 is V. 6 is VI. And 7 is VII. Obviously, your Roman numerals go way past this, but you only need to know 1 through 7. And when I say know them, I mean actually know them, be able to understand them, be able to use them. You need to memorize them. Couple of exceptions, because everything good in chemistry has some exceptions. There are 3 transition metals that do not have variable charge. Zinc is a transition metal, but it always has a +2 charge. Silver is a transition metal, but it always has a +1 charge. Cadmium is a transition metal, but it always has a +2. Again, you're going to need to memorize these. They don't follow a pattern, so you won't be able to just use the group on the periodic table to know what they are. But since they don't have variable charges, you won't be given the charge in the form of a Roman numeral. You just have to know it. So those are 3 transition metals that do not have variable charge. And on the flip side of that, we have 3 representative elements that do have variable charge. Tin, Sn, lead, Pb, and antimony, Sb, are technically representative elements, but they don't follow the charge at the top of the group. They have variable charge. It will change, so these will have Roman numerals. Little summary on our table. Again, remember we have +1 on our alkali, +2 on alkaline earth, +3, skip, -3, -2, -1, 0. And that's all we talked about before, but now we can talk about our transition metals a little bit. So remember, those are right between these 2 columns. Cadmium is one of your special cases. Cadmium is right here, and it's always a +2. Zinc is a special case. It's right here. It's always +2. Silver is always +1. And again, we also have 3 representative elements that do not follow the rules. These 3 elements here are your 3 exceptions: lead, antimony, and tin. They do not follow the charges that are listed at the top of the table. Besides that, besides the variable charges or the not variable charges, writing formulas for transition metals is exactly the same as what we were just doing. So let's see some examples of this. All right, so just like before, we are going to write names for the formulas we are given, and we will write formulas for the names that we are given. Names to formulas are just a little bit easier, but even formula to name is not bad. All right, our first one here is iron 3 oxide. So the 3 goes with the iron. It is saying, you see this iron here? This iron has a 3+ charge. We don't need a Roman numeral for oxide because oxide is always O2-. So then we can say that if we have 2 irons, it would take 3 oxides to cancel them out, and we would get 0. And again, if you still need to draw out your charges, that's fine too. We start with 1, 2, 3 positives from iron and 1, 2 negatives from oxygen. We don't have enough negatives, so we'll add another oxygen. That'll give us 2 more negatives. So that's an oxygen, this is an oxygen, this is an iron. But with 2 oxygens, now we need more positives. We need another iron, which always comes in sets of 3. So we'll draw 1, 2, 3 more positives from a second iron. And now we have too many positives, but if we add 1, 2 more negatives from oxygen, then we will have 6 positives and 6 negatives, 2 irons, 3 oxygens, Fe2O3. And again, this is not read as iron oxide, it's read as iron 3 oxide. All right, 1 down. Let's look at our next name to formula. We are told it is copper 2 sulfide. And again, the Roman numeral goes with the metal. Metals always form positive charges, so copper 2 must be Cu2+. And then sulfide is always S2-. So here, since we have 2 positives and 2 negatives, we'll just need 1 of each to cancel out. 1 of our positive 2's plus 1 of our negative 2's will add up to 0. So copper 2 sulfide must be Cu S, just 1 of each. All right, let's go the other way. Let's take a formula and write a name. So we know that we have some kind of tin here, and we know that we have chlorine, which forms the chloride ion. So this is definitely going to be tin chloride, but we need to know what the charge is on tin, because remember, tin is one of your representative elements that has variable charge. So we know that the chloride ion is Cl-. We need to figure out what the charge is on this tin ion because whatever the charge is, we can put in these parentheses as our Roman numeral. So we're going to actually set this up the same way we've been doing our math, but we're going to plug into a different place. We know that we have one tin because it says right here just SN. There is no subscript, so the implication is that there is one tin right there. So we know that we have one tin. We don't know what its charge is. Charge is unknown. But we know that when we add it to 4 chlorides, right, because 4 chlorides, and when each of those chlorides has a -1 charge, as they always do, this has to add up to 0. That's how ionic compounds work. When you add up all the charges from your cation plus all the charges from your anion, it has to be 0. So we can use this to find the charge of tin. Just doing a little algebra. 1 times x is x. 4 times -1 is -4. And this needs to equal 0. So if x minus 4 is 0, then x must be 4. That tells us that the charge of tin is 4 plus, and if the charge of tin is 4 plus, then this must be tin 4 chloride. A little convoluted, but if you can keep the steps straight, you'll do it fine every time. Let's look at one more of these before you practice on your own. All right, our next one here, same thing. We have lead, which is technically a representative element, but it's one of our representative elements that can have variable charge. So we know that this is going to be lead something oxide, but we don't know what the something is. What we do know is that we have a single lead ion of unknown charge, and we know that we have 2 oxides that each have a 2 negative charge. So we can set our math up again. 1 lead times, we don't know what the charge of lead is, plus 2 oxides times the charge of each oxide is -2 should equal 0. Then we'll do our algebra. 1 times x is x. 2 times -2 is -4. So x minus 4 is equal to 0. This should be looking pretty familiar. X is equal to 4. So that means that this lead has a charge of 4 plus, which means that this is lead 4 oxide. It's not always 4. It just worked out that way here. All right, so down at the bottom of the page, you have 6 practice problems, 3 name to formula, 3 formula to name. Go ahead, pause the video, work those out, and when you're ready to check your answers, unpause. Hopefully this is what you got for those. If it is not, go back, see what you did. If you need to, draw out those positives and negatives, write out that algebra, see if you can't figure out where you went wrong. Once you're feeling good on those, keep going. We have one more type of ionic compound to talk about, and those, as you may recall, are the hydrated ionic compounds, or as they are more commonly known, hydrates. Your hydrates are ionic compounds like potassium chloride or sodium sulfate, but within their structure, they contain a specific number of water molecules, right? Hydrate means water. If you need to stay hydrated, you should drink water. As far as naming your hydrates, it's really not anything too new. They're always going to be in 2 pieces. There will be an ionic part, and then a dot, and then a number, and then H2O. This is how your hydrates are written always. So the first thing you will do is name the ionic compound as usual. Whatever this compound is here, you will name it the ways you've learned in this video. Name the first thing, name the second thing, metals, nonmetals, polyatomic ions, all that good stuff. name the ionic compound as usual. And then for the second part, indicate the number of water molecules using the Greek prefixes that we learned in the last video with covalent naming. So remember that the prefix that means 1 is mono, the prefix that means 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. So putting this into practice, 2 examples here. Copper 2 chloride dihydrate. Again, do it in 2 pieces. It's going to end up looking like this. It'll be an ionic compound, and then a dot, and then a number, and then water. So let's just focus on the ionic compound first, copper 2 chloride, and we'll just ignore the dihydrate for a second. Copper 2 is a transition metal. It's telling us it has a 2+ charge. So copper 2 is Cu 2+. Chloride is Cl-. Chlorine always forms a -1 charge. So then we're going to need 1 copper and 2 chlorides, and the ionic part of this will end up being CuCl2. So this is copper 2 chloride. Now that we have figured out that this is copper 2 chloride, now we can focus on the second part. So let's unscribble our water here. So we have CuCl2. We will draw a dot to indicate that we're not quite done. And then we have dihydrate. This di means 2, and this hydrate means water. So the way that you write this formula is CuCl2 dot 2H2O. Going the other way, again, we'll follow the same rules as always. Look at it in 2 separate pieces. First, let's just name this ionic thing. This metal right here is magnesium. This ion here, this SO4, that is sulfate. And now that we have named the ionic, now we can focus on the hydrate. We have 7 waters. So the way that we say 7 is hepta. And the way that we say water is hydrate. So MgSO4 dot 7H2O is magnesium sulfate heptahydrate. Kind of a mouthful, but shouldn't be too difficult because it's just a little bit tagged on to the end. All right, you've got a little bit of practice down here at the bottom. Go ahead, give that a go and see when you're ready to check your answers. Unpause the video. All right, hopefully this is what you came up with for your 2 names and your 2 formulas. There is a whole lot more practice after this. There are 6 problems at the bottom of this page and then many more on the next page. So those answers are not in this video, but they are posted on my website. Work through that practice, see how you can do without cheating, without looking at the answers, and when you're ready to check yourself, go over to my website, check out the key for ionic naming, and see how you did. If you're feeling good, you can move on and start learning about molar mass and return to moles. If you are not feeling great about these, maybe watch through the examples one more time or head into tutorials, get a little bit of help. But either way, good luck and happy studying.